Today, we're going to talk about SPC. What is it and why is it important? So what's the objective here? Again, as I said, we're going to talk about what SPC is and why it is needed. Quality core tools. For those who have never heard of it, we do have 5 topics which are called core tools, quality core tools in automotive. They're actually AIAG publications. So APQP with control plan, PPAP, FMEA, MSA, and SPC. Actually, a couple of weeks ago or so, we did talk about the process FMEA. And today's topic, we're going to talk about SPC, the Statistical Process Control, which describes the several basic and advanced statistical methods to ensure process improvements are as effective as possible. Now, the ultimate goal, before we get into the SPC part of it, I wanted to point out the linkage between APQP and the quality. The ultimate goal of APQP is customer satisfaction, and one can achieve this by applying APQP, where APQP will assure robust designs, producible products, capable processes, timely production, and on-time delivery. So before, again, we get into more on the statistical process control, we need to define what process control is about. Process control is the most important component of the quality effort during manufacture, and its objective is to proactively evaluate the condition of a process and to control it as to prevent the production of defective units. The term process parameter is important here because it's used in quality literature to indicate both the variables of a process that influence the product characteristics, as well as the quantities that define the distribution of a process, such as the mean and the standard deviation of a normal distribution. Any productive work can be viewed as a process consisting of machinery, manpower, methods, measurement. As you can see in the picture here, you have all the inputs, in this case material, within a given environment, right? It's certain temperature, humidity, and all that. But going through the machinery, and you need the machinery, manpower, methods, and measurement, and then there will be some kind of an output, which is the product. Dr. Walter Sheward, a little bit history about SPC. In early 1920s at the Bell Telephone Laboratories in Princeton, New Jersey, proposed the procedures that later came to be known as the control charts. According to him, the variability in a product characteristic or process parameter can be from 2 sources. From a common cause or stable system of chances, meaning the aggregate of small unavoidable variability arising from natural differences in material, manpower, machinery, instruments, and the environment that should be expected. Or from special cause or assignable causes, meaning arising from a specific occurrence such as broken tool, pressure surge, or temperature drop that might occur unexpectedly. So this, again, we're going to be dealing with 2 types of variation that are going to be either common cause or special cause variations. So this is a typical control chart, which has a center line, which is the process mean, and the 2 control limits, as you can see, upper control limit and the lower control limit. So again, these are not the spec limits. These are control limits defined by the process mean And these are actually the upper control limit is the mean plus the 3 standard deviation, and the lower control limit is mean minus 3 standard deviation. So within this range is what we expect all the data points be falling into. And all these dots that you see here are the data points. So now that we know the structure of a control chart, SPC is a method of measuring and controlling quality by monitoring the manufacturing process. Quality data is collected in the form of product or process measurements or readings from various machines or instrumentation. The data is collected and used to evaluate, monitor, and control a process. SPC is an effective method to drive continuous improvement. So by monitoring and controlling a process, we can assure that it operates at its fullest potential. And as you can see here in this picture, the process control system model with feedback starts with the voice of the process, right? And we do have statistical methods, as we talked about before, people, equipment, material, methods, measurement, environment, those are all inputs. The way we work and blending of resources, products or services going through, and those are your outputs, right? So you have the inputs, the process, their system, and the outputs. And of course, the customers, where we identify the changing needs and expectation. So from that, every increase in competition, along with raw material costs going up, companies concentrate on what they can control, which is their processes. Companies must strive for continuous improvement in quality, efficiency, and cost reduction. Many companies still rely only on inspection after production to detect quality issues. The SPC process is implemented to move a company from detection-based to prevention-based quality controls. By monitoring the performance of a process in real time, the operator can detect the trends or changes in the process before they result in non-conforming product and scrap. So before implementing SPC, the manufacturing process should be evaluated to determine the main areas of waste. It would be most beneficial to apply the SPC tool to manufacturing process waste that are rework, scrap, and excessive inspection time. During SPC, not all dimensions are monitored due to the expense, time, and production delays that would incur. So SPC should be implemented for the key or critical characteristics of the design or process identified during DFIMA and or PFIMA. DFIMA stands for Design Failure Mode and Effects Analysis. PFIMA stands for Process Failure Mode and Effects Analysis. These are the two risk assessment tools we use with product and the process, respectively. Data would then be collected and monitored, and on those key or critical characteristics. SPC is so important that, again, it's important to reiterate here that it should be implemented for the key or critical characteristics of the design or process. How to implement it? The flow chart you're going to see here is actually two parts. It was an eye chart when I tried to put it all in one slide. This is going to be the right outlines, the outlining the major components of an effective SPC effort. So it starts with defining the measurement method, then the qualify the measurement system. From there, we need to initiate data collection and SPC charting, then developing and documenting the reaction plan. So that's step 4. Step 5, adding chart to control plan. And step 6, calculate the control limits after 20, 25 subgroups. 7, assessing the control. It's right here, reaction plan. 8, analyzing data to identify the root cause and the corrective action. 9 is design and implement actions to improve process capability. 10, calculate the CPC-PK and compare the benchmark. And last but not the least is the last step is to monitor and focus efforts on next highest priority. So again, this may be a little bit confusing, but in reality, those are the steps that we follow to implement SPC. So again, as I said before, there are different types of variation that we have to deal with. If you look at this picture right here, as you can see on this chart here, pieces vary from each other as the size is different, right? And then, but then they form a pattern that, if stable, can be described as a distribution. So, and again, depending on the size, you can see how that distribution actually becomes, in this case, actually, it's a great example of a normal distribution curve. Distribution can differ either in location, that means what happens to the center of your process, or the spread, which is the shape of your distribution. In other words, the amount of variation. And the shape here, if you can see, it could be skewed to the right or left, depending on, again, where the majority of your data points are. So you may actually have maybe data points that are above the, center, close to your upper spec limit versus, the natural expectation of having the randomness around the mean. If only common causes of variation are present, the output of a process forms a distribution that is stable over time and is predictable. As you can see, the distribution over time, the curve is almost identical. And because of that, it's easy to predict the future of that. If special causes of variation are present, the process output is not stable over time. So as you can see here, looking at the variation in this time versus that time, it's less, and this time it's skewed, and here's you have a larger. So based on that, the target line, as you can see here, it's unable to predict because you don't have a consistent, right, variation over time, so that we could be able to predict the future. These are great examples of processes. Again, if you look at over time what happens with, this is a good example of out of control situation. Sorry, let me go back. And this is a great, see, you only deal with the common cause there, and they tend to be stable and in control. So we use the stability and in control interchangeably. So it means the same thing. As for the process capability, as you can see here, in control but not capable of meeting specification. So that means variation from common causes is excessive. Here, that's what happens here, the first three curves, right? And then these top three seems to be in control and capable of meeting specs. And the reason I'm saying that these dotted lines here in this point are representing spec limits, not the control limits. Since my distribution, actually I have data points that are outside my spec limits, that's why I call them on, they're not capable. So Control charts, some guidelines that I wanted to provide you here. SPC is not a PPAP element. As you know, a PPAP production part approval process. And it's not a required element, but plays an important role in determining the process capability and in keeping the process in control. So control charts should be used when the process is new. Control charts must be used to determine if a process is stable before its capability can be assessed. So it doesn't make sense to calculate the CP/CPK knowing that the process is not stable yet. And the control charts for process KCs or key characteristics should continue to be used throughout ongoing production. So now let's closely review the definition of the special cause. And we have some tests that we apply to determine if the process is stable or not. There are like 8 tests that we're going to apply each time. I'm not going to get into the detail of which tests are applicable to what type of data or variation you're dealing with. Overall, I want to point out these 8 tests. And if any one of these tests apply to your control charts and it fails, that means your process has a special cause and needs to be reacted on. So the first one, we call it 1 point outside the control limits. So in other words, outside 3 sigma from the center line, right? So these red lines are your control limits, and we do have a data point. And by the way, these charts, Minitab, it's a software, if you haven't heard of it, it's a great statistical analysis tool or software that we use, and I'm used to, and I use that whole a lot. And I took actually these graphs from Minitab defining each of these tests. So, and as you're gonna see actually when it happens, when you do the control chart, so when you see these numbering schemes on the control charts, it actually means something. 1, 2, 3, 4 means that, oh, it's failing the test 4, failing test 3, and so on and so forth. Can you have a chart where you will have multiple tests be failed? Of course you can, but in order for us to clearly define each test, I just wanted to point out them individually so that you can see how the tests are being conducted. The second test says here 9 points in a row on the same side of the center line. So if I count, so I go from top to bottom, right, below the center line. So it's 1, 2, 3, 4, 5, 6, 7, 8, right there. That's my 9 points. It says again the same side of the center line. It doesn't say 1 standard deviation, 2 standard deviation, or 3 standard deviation below the center line. It says if you have 9 points in a row on the same side of the center line, you have a special cause that you need to react on. The test 3 says 6 points in a row, all increasing or all decreasing. Okay, I do have decreasing trend here. So there's 1, 2, 3, 4, 5, 6. Or I have 1, 2, 3, 4, 5, 6, 7. So you do have actually 2, but I think yeah, it seems 1, 2, 3, 4, 5, 6. Sorry. So this one is 1, 2, 3, 4, 5. And this one is 6. That's why we're saying, okay, here's your special cause. Test 4, 14 points in a row, alternating up and down, up and down. So what does that mean? Again, for the randomness, right, you would expect data points all over the places. But if you look at here, the trend is that we have data point going down, going up, down, up, down, up, down, up, down. When that happens 14 times in a row, that means there's a special cause that, again, we need to investigate and find out what's happening there. Test 5, it says 2 out of 3 points, more than 2 standard deviation from the center line. And now this case, it says on the same side. So 2 out of 3 points. So if you count 1, 2, 3, 4, 5, right? So I have 1 below and 2 above. So 2 out of 3 is above the center line. Same thing here. You have 1, 2 out of 3, 1, 2, 3. So 2 out of 3 is on the same side. So, and then the test 6 says 4 out of 5 points, more than, something's wrong here. I apologize. I think this chart is not the correct chart. I'll have to fix that. But it says 4 out of 4 points, more than 1 standard deviation from the center line. So assume this is, so remember earlier I mentioned this is the 3 sigma line, upper control limit. So that means you would have 1 standard deviation and 2 standard deviation in between, so another 2 zones, we call them zones. So we would expect 4 out of 5 points are being outside of that center line. So that's how we define the test 6 result. And this one is also test 7. As you can see here, it says 15 points in a row within 1 standard deviation of center line. So if we count, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 15. Again, it's within that 1 center line, either side, by the way. So that's why it fails the test. This one here says 8 points in a row, more than 1 standard deviation from the center line. And I apologize, I think I do have another chart problem here. This is not reflecting what 8 points is about. So I need to fix that as well. But I think you're getting the point here is that we do have 8 tests. So whenever we have a control chart, we need to, we need to test them all out and making sure that we pass all these tests. You may be asking, so how am I supposed to, remember all these? Well, you don't. That's why I mentioned earlier, Minitab. When you do your control charts in Minitab, Minitab will actually point them out for you, like how they are pointed out in here. So in real life, you will have, like the red box like this to pointing out, okay, you have a special cause here, special cause there. So we do have different types of control charts, and sometimes it's challenging to know which control chart to use. And I think this one right here is a great way to show you which chart to use. So when you have a continuous data, in other words, quantitative data, then the next step is that you need to decide, okay, you need to define what your sample size is. If you're only measuring 1 data point at a time, the chart that you're going to use is called either XMR or IMR, individual moving range charts. If you are using the sample size of 2 through 10, you will use X bar and R chart. When you have greater than 10, sorry, this one is also a typo there, then you expect to be using X bar and S chart. You may ask, okay, what's the difference? Again, for the sake of time here, we don't have the time to explain all the charts types and their differences, but there is a summary slide at the end I'll share with you that will kind of compare when and how we use each of these charts. So that's when you have a quantitative or continuous data. When you have attribute data, then it is going to be depending on the defects. If you have one defect per unit, and if the sample size is constant, which means every time you measure or you inspect the same number of parts, then you use the chart called NP chart. If your sample size is not constant, that means first, for example, batch, maybe you're testing or measuring inspecting 5 parts. Next time it's 7, next time it's 20. That means you're not sampling constantly. At that point, you're gonna use P chart. Now, if you have multiple defects per unit, again, depending on the sample size being constant or not, you're gonna use either C chart or U chart. Here's one quick example I want to share with you. This is a fictitious exercise, by the way, an example. So, and yeah, it doesn't necessarily reflect a reality, but it really makes sense to showcase how SPC can be used. In this case, PMC received some complaints about narrow misfitting gaps between the upper and the lower window sashes. The plant manager wants to evaluate the capability of a critical cutting operation that he suspects might be the source of this gap problem. Excuse me. The nominal specs for this cutting operation is 25.500 and inches with a tolerance of 30 thou. Inspect 5 consecutive window panels in the middle of each shift over a 15-day period and recording the dimensions of the cut. So 5 consecutive window. So what does that mean? Our sample size is 5. So looking at this right here, and again, you're measuring, so it's quantitative or continuous data. The sample size is between 1 and 11 and 1 and 10. So we're going to use X bar and R chart. Here's the actual data. Okay, 15 days it was collected. So when we did let's look at the bottom chart first. When we charted out the X bar, we're seeing actually 3 data points that are out of the control limits, right? So it fails the first test. And then when you look at the ranges, there is only 1 data point 24 failed the special cost test. So in this case, we say our process is out of control. So here's what we do though. When we identify those special causes, we look at the data points that we measure them, we do investigation, we find out, again, since it's a special cause, right? So we tend to fix them right away. So when we fix them, and for the sake of process stability, we can remove these data points. So when we remove them, here's what happened. Now, my both X bar and the R charts are within control. Now you may ask, hey, did we use the other 7 tests? Yes, this is done in Minitab, and that's why the Minitab did all the tests for me, and I don't have to, and there's nothing that Minitab is pointing out it's out of out of control for. So there's no special cause anymore. Here's another example of, remember, when you have a continuous data, you have 3, but 2 when you have a sample size greater than 2, right? 2 options. Between 2 and 10, it's X bar and R chart, and between, greater than 10, we use X bar and S chart. And this point, if you remember, R means the range. In other words, the difference between the max and the minimum, right? Data point, and the S is actually standard deviation. So that means we're actually calculating the standard deviation of each subgroup and comparing those, and which gives us a little bit better detail of our data points. And for that, it's, in other words, this is more powerful. And this one actually is showing that we have one data point that was out of spec, failing the first test. Here's another example of a p-chart. And again, as you can see, what happens to your control limits. Remember, a p-chart is used when your sample size is not constant. So, and that's why we have that also, again, the upper and lower control limits not steady. So we do have actually two data points where this is out of control. There's a C chart based on the original data. Again, it's pointing out one data point being out of spec. Here's a good one for C chart being in control. Nothing is out of spec. This is the one that I mentioned earlier, the control chart summary, where applicable, also known as based on the assumption and usual sample size. Again, this may not, depending on the statistics books that you read, you're going to find out these numbers may be slightly different. And based on my experience, I think what I had used in the chart earlier, the roadmap is actually very wisely used. So in this case, where again, X bar in our chart is applicable for controlling the average and the variability of a measurement, also known as the measurement control chart, based on the assumption of normal distribution for a measurement. So for that reason, actually, even though we assume data is normal, but we usually test for that normality to make sure that data is normal. And then again, usual sample size, and anything, n is greater than 2 through 10 is actually great to use in this case. And then the P chart for controlling the fraction defectives in a process. And this one is also known as the fraction defectives control chart. And this one is based on the assumption of binomial distribution for the occurrence of defectives in a sample. And this one we're going to use when n is greater or equal to 20. And the C chart is for controlling defects per unit or unit length or unit area and so on. And it's also known as the defects per unit control chart. Poisson distribution for the occurrence of defects in a unit is what it's based on. Again, use the unit size to obtain the lower control limit greater than 0.